In this video, I'm going to talk about perhaps the simplest kind of problem in time-dependent quantum mechanics. That is a problem of a sudden perturbation. So, which happens when a potential in a quantum problem changes very fast as compared to all other relevant timescales in the problem. So, another term for such a sudden change in the potential, is a quantum quench. So, and this may happen, for instance, if we have a potential which changes very rapidly from one form to a different form. So let's say here, for example, I'm showing a harmonic oscillator potential, and let's say for a negative time, we have a particle, let's say, just sitting here on a stationary state described by the usual Gaussian wave function, which is the eigenfunction of the ground state wave function of the harmonic oscillator. And let's imagine that at t equals 0, the frequency of the harmonic oscillator potential changes rapidly, so it increases rapidly, such that it becomes a completely different potential now. So what kind of questions can we ask? So before asking questions, let's see what's going on here. So the main sort of insight in this problem is that while the potential changes very rapidly, the wave function does not have the time to change. So the wave function right before the quench is exactly equal to the wave function right after the quench, in the approximation of an infinitely fast or an infinitely sudden quench of the potential. Let's say in this case from one harmonic oscillator frequency to a different harmonic oscillator frequency. So, but another important insight is that the quantum state that used to be a good, stable, stationary ground state is no longer an eigenstate of our potential. But what is it? So this wave function, the old wave function, is just some wave function from the point of view of the new Hamiltonian. So, for instance, let me call this guy here psi naught 1, which refers to the ground state of the old potential that we had for negative for t smaller than 0. And now, after we quench it, so this psi naught 1 is no longer an eigenstate of the new Hamiltonian. Let's say we have this Hamiltonian H2. When it acts on psi naught 1, it's no longer equal to an energy of anything times psi naught 1. So it's no longer proportional to psi naught 1. So this state is no longer an eigenstate. What it is, though, it's as always, we can use the eigenstates of the new Hamiltonian. So we can use these eigenstates as a basis. So what we can expand our wave function, which was the eigenstate of the old Hamiltonian, in terms of the some coefficients here. Let me call it C sub n, and n in this case goes from 0 to infinity, in this particular case of harmonic oscillator. So, and this can be expanded in terms of the wave functions of the new harmonic oscillator Hamiltonian. But in general, these coefficients are all non-zero. So what happens after we do this quench is that the wave function, which used to be a nice pure state with a well-defined energy, well-defined frequency, now becomes essentially a bunch of incoherent harmonics with different frequencies. It's something, if I were to suggest a possible classical analog of what happens here, imagine you have a guitar string and you generated a pure frequency, pure sound with the natural frequency of the string, and then you suddenly change the length of the string. Just pinch it at a certain distance. So then you're going to generate all kinds of new sounds, all kinds of harmonics. It's no longer going to be a pure sound. A similar thing is happening here, but instead of the sound, instead of the strings, we're having quantum states which become now a linear combination of the new eigenstates. So an interesting illustration perhaps of a physically relevant phenomenon that can be discussed in this context here. So let's say, again, let me go back to this original potential. So let's say we have many particles sitting on the ground state, in the ground state. So this basically means that there is a Bose-Einstein condensate of sorts, which are produced routinely in many experimental laboratories worldwide. So this is now done very frequently and routinely. So, and let me say I change the frequency of the trap as I just showed you. So, and what happens is that these particles which used to be in the ground state of the old potential, they now get redistributed to essentially all possible states of the new potential. And after time goes by, so there is some relaxation going on, and the system relaxes to a new state, but now the temperature of the state is going to be larger, because the temperature is actually essentially the measure of the typical energy of a particle in a many-body system. So essentially what I'm saying here is that any change in the potential, in this case is a harmonic oscillator, but it's completely a general statement, any sudden change of the potential always hits it up. So it doesn't matter whether we increase the frequency or decrease the frequency. If we, let's say, had the lowest energy state in the beginning with the lowest possible temperature, let's say even zero, absolute zero in this model, if we do the quench, so the particles are going to be redistributed among all possible energies, and eventually they're going to relax to a finite temperature, which is always higher than the original one. So this is an interesting phenomenon that we can understand without any calculations, just by this discussion. Now, another thing, let me just mention in the end. So here, in the context of this expansion of the original wave function in terms of the new eigenfunctions of the harmonic oscillator, well, or any other potential for this matter. So these coefficients determine the probability of us finding the particle in the single particle case, or the density of particles, let's say, in the many particle case, in a specific new eigenstate. So Cn squared is exactly the probability of finding our particle in the state psi sub n2. 2 again refers to the potential after the quench, well, at t greater than 0. Okay, it's not always working, this writing on a tablet. Now let me move actually to a similar but physically quite different problem, which also involves a sudden perturbation, but it's a perturbation of a completely different type. So the toy problem that we're going to solve was actually a serious research problem back 70 years ago or so, in the good old days of theoretical physics, and it was actually conceived by a famous Russian theorist, mostly working in nuclear physics, Arkady Migdal, in 1939. So this problem I'm going to discuss actually appears also in the Landau-Lifshitz course on theoretical physics, for those of you who have access to this material. Well, the problem itself is quite straightforward, so to formulate the problem. So let's say we have an atom. So for the sake of simplicity, I'll be talking about a hydrogen atom, but in principle we can consider any atom, including heavy atoms, for which it's the most interesting due to various applications in nuclear physics. And let's imagine that a nucleus of this atom, which has its atomic electron or electrons in its ground state, receives a sharp impulse which gives it a velocity v. So we kick it with a radiation or with a hammer, or we drop it from an airplane or whatever you want to think about. So, and what we want to know is what's going to happen with the electron. So basically here the sharp sudden perturbation is that initially we have this atom at rest, and at a certain moment of time, let's say t equals 0, this atom starts moving with a certain velocity v. And as it does so, we want to follow it, and we want to see if the electron gets excited. But how do we calculate the probability for the electron to get excited? That is to say that it would go to an excited state with the higher quantum number, or the atom would even get ionized. That is to say that the electron just leaves the atom and goes into the continuum, and they just go two separate ways, the atom, the nucleus, and the electron. So here, naively, it seems that the potential doesn't really change. We don't quench the potential. But if we look at this problem a little closer, we see that, well, the atom, when it receives this impulse or this kick, so the atom starts moving, and the atom is the potential which binds the electron to it in the first place. So therefore, the potential in which the electron is supposed to be bound starts moving. And so this is a sharp change. And so the original, but the wave function of the electron does not have time to change. So if, let's say, the electron was here in the vicinity of the lowest orbit, so it was localized in the vicinity of the lowest orbit, it will just try to stay there. And the question we're asking is whether the atom, when it starts moving with a certain velocity, whether it will carry the electron with it, or whether it will leave it behind, or maybe whether the electron will sort of dissipate into higher energy states. So, for this, to solve this problem, what turns out to be useful is to go into another frame of reference, which is moving together with the atom. So essentially, we want just to move together with the atom and write the wave function of the electron in this new frame of reference. So this is really the key to solving the problem, because in the frame of reference moving together with the atom, the potential is exactly the same. It was the Coulomb potential to begin with, is the Coulomb potential here, and in this frame of reference, the atom, the nucleus itself is static, but the electron now is moving. And so essentially what we have to do, we have to write the electron wave function after the quench, well, in this case it's not a quench, I'm sorry, I shouldn't have said that, after this sort of jolt of the atom, this wave function will have two pieces. So the first piece is going to be just the standard ground state wave function of the hydrogen atom, in the case of hydrogen atom, and there will be a piece, a new piece, which is related to the velocity of the electron moving with velocity v. So here essentially it's a plane wave. So a way to write the wave function in the frame of reference moving with the nucleus is to write it as a product of a localized wave function in the lowest orbit times the plane wave. And here again, this mv is simply the momentum of the electron in this frame of reference, and this is just the standard plane wave expression. So now the final step is to calculate the excitation probability of the electron, that is to find the total probability of the electron going to some higher energy state, including the continuum states. And well, the good thing is that we know the wave function now. So in this moving frame of reference, let me just write it again. So psi naught of r is equal to 1 over the square root of pi a cubed, so this is the Bohr's radius, e to the power minus r over the Bohr radius, and times this plane wave, e to the power minus I over h bar mv dot r. So this is our wave function we just derived, sort of, which is by logical reasoning. And if we want to know, let's say, what the probability of a transition into a higher energy state is, let's say some other state, I'm not going to specify what it is, but some, let's say psi sub k, whatever k is. So k could be a collection of indices involving the radial quantum numbers and the angular quantum numbers, or it can be a label of a continuum state, whatever this label, quantum label is. So the amplitude, the transition amplitude, is going to be, let me write it, a of 0 to k will be equal to the overlap integral of this psi naught, let me write it star, although it doesn't really matter, psi sub k of r integrated over the volume. And the probability to go from this ground state to an excited state, w sub k, is going to be equal to the absolute value squared of this transition amplitude. So this is what it means. So another way to connect it to what I talked about previously is to notice that this wave function can be expanded in the basis of all eigenstates of our problem. In this case, actually, it's both the discrete states, which describe electrons localized near the atom, and also the continuum states. Okay, and it seems that, well, the problem is very complicated, so we have to sum over all these probabilities. But, well, fortunately, we don't have to do so, really, so this was just an unnecessary comment. As a matter of fact, if we're interested in calculating the total excitation probability, we may want to notice that the total probability to find the electron in some quantum state is equal to 1. So the electron will stay somewhere, right? So it will be in some state. So therefore, the probability to remain in the ground state plus the excitation probability, which is essentially the sum in some generalized sense, it also involves an integral of this w sub k. So this must be equal to 1. And this excitation probability is exactly what we're trying to find. So from this equation, we simply can write that this excitation probability is equal to 1 minus the probability not to get excited, the probability to remain in the ground state now of the moving atom, of the moving nucleus. Well, I just realized actually that there is a slight problem with the notations here, because what we're actually looking for is the transition amplitudes and the transition probability from an electron that is a moving electron relative to the stationary nucleus, but we want to find transitions amplitude into a stationary states localized near this nucleus. So therefore, these states, for instance, they do not have this plane wave piece. So let me just introduce a tilde here, which would refer to the fact that these guys are moving together with the atom, while this state psi naught that we derived in the previous slide is actually moving with the velocity v relative to the atom. Now, with this correction to notations and with this comment about the total probability of staying in the new ground state plus the probability of excitation being equal to 1, we can write down this excitation probability. Let me just do that. Psi star is going to be equal to 1 minus the probability to stay in the ground state, which means that I have to take this integral of psi naught with psi naught tilde. This is the ground state of the stationary atom, integrate it over the volume and square the absolute value of it. And so here I know everything there is to know. So for example, this part here is exactly this psi naught tilde in my new inconvenient perhaps notations. So we can just plug in these functions and integrate over the volume, and I will leave this calculation to you. So let me just maybe write an intermediate step and the final result. So the intermediate step would simply involve writing down explicitly this integral. So it's going to be 1 minus 1 over pi a Bohr radius cube. So from the normalization factor in the ground state wave function times the exponential, well, integral of the exponential minus 2r over the Bohr radius minus this plane wave I over h bar p dot r. And so integrate it over the volume and everything is squared. So this is really the integral that needs to be calculated. Well, I could take another 5 minutes to go with you through the calculation of the integral, but I think it's probably not the best use of your time and my time too. So let me just leave it for those who are interested to do it on your own, and let me just write the final result. So the final result will be this: 1 minus 1 divided by this ratio here, 1 over 4, m v squared, m squared v squared, a squared. This is the Bohr radius divided by h bar squared, and everything to the 4th power. So I'm not necessarily saying that this is the most important and illuminating result in physics, but it's a result. It's something we can actually measure and check. So what happens if we kick an atom? So what is the probability of it being excited, and therefore it would emit photons, and there are all kinds of different phenomena associated with it. So, and one can run various anti-checks on this result. So let's say if the velocity is 0, so we don't really kick the atom, so it was stationary, it remains stationary, we have 1 minus 1, so the probability to excite the atom is exactly 0, as it should be, because we don't really do anything. On the other hand, if the velocity here, well, in our non-relativistic case, goes to infinity, so the 1 over infinity is 0, so the probability to excite the atom is exactly 1. So we just will leave the electron behind. That's what's going to happen. The nucleus will just go away. That's what's going to happen. In any case, so this is just an example that I wanted to show you. So actually 2 examples in this part of time-dependent quantum mechanical problems. And in both these cases, we dealt with very sharp, very sudden perturbations to our Hamiltonian, and they resulted in a redistribution essentially of energy. So the energy of the original state was, well, the original state of the old Hamiltonian became a linear combination, a rather complicated linear combination of eigenstates of the new Hamiltonian. And this is very typical for sharp perturbations or non-adiabatic perturbations. Now in the next video we're going to study actually the opposite case of a very slow perturbation or adiabatic perturbation, which in some sense is more interesting in that it involves new mathematical structures and new phenomena, so-called topological Berry phase, which is currently actually the subject of intense research in condensed matter physics.